Welcome back to lipids in our biochemistry discussion. We talked about some delicious sugars, carbohydrates last time, and today we're going to be talking about delicious fats and lipids and understanding what lipids mean and just the really interesting role that they play in our bodies. So, what do you guys think of when you think of lipids? To me, I sometimes I think of oils or something that doesn't mix with water, and that's true. But lipids are a very broad classification of compounds, and yeah, they are all insoluble in water, so they do not mix well with water. So that really helps dictate their properties in our bodies and things like that. So this photo just shows a whole bunch of examples of what we mean by lipids. We have oils, fats, a Crisco over here. We've got membranes in our cells. We've got hormones that in the form of steroids, soaps, things like that. These are all part of the broad classification of lipids. So we are going to be looking at the triglyceride version of lipids first. And these are what they say here, triglycerides. So it's a glycerol molecule and then 3 fatty acids tied together to form a triglyceride. That's how we store fatty acids in our body. And we use these for energy and insulation, things like that. So let's take a look at, well, we'll take a look at that in just a second. But let's talk about fatty acids in general. And we're going to be seeing them drawn a lot in the skeletal structure formula like this. So we have this long non-polar chain of carbons, and then we have a carboxylic acid group over here, and we call these fatty acids. You might see them drawn in their condensed form like this, or even more condensed, but typically we'll be seeing drawn like this. So we can see that we have, this one's fully saturated with hydrogens. There's no double or triple bonds. So this would be a saturated fatty acid. And if it has any amount of double bonds, it would be an unsaturated fatty acid. And the double bonds that naturally occur in fatty acids are cis, the cis variety, not trans. There are a small amount of naturally found fatty acids that are trans, but they're very rare. It's very uncommon to find. And if you do, there's very few of the trans bonds found. So you can build these up using that lipids tab of the biomolecules activity that's linked here in the PowerPoint once you get to that point, or it's in your book just right away. So you can check that out if you'd like. But let's build one. So glycerol is the backbone. I talked about this briefly in the first lecture. This tri-alcohol propane group with 3 alcohols, we call it glycerol. And you take 3 fatty acids and we store them together and we form these ester linkages. So notice this is a combination of 3 different fatty acids. This one is a 14, 15, 16 carbon chain coming off of this, so I guess 17 total. This has 18, so 16, 17, 18. There's an 18 carbon chain. Both of these are unsaturated. This one, on the other hand, has a double bond at the C8 to 9 position. So, but we can have a variety of these. So overall, we form this triglyceride, and we find 2 saturated fatty acids and 1 unsaturated. Notice the acidic character goes away. Before, these act as weak acids in water, and they're not very soluble because they still have these really long chains, but these are much more soluble in water than a triglyceride would be because you're losing that really polar end, the carboxylic acid end. Now it's tied up in this ester bond, and we also lose 3 waters. So this would be the triglycerides that we find in fats and oils. And we're going to define what fats and oils are too. So, but in our bodies, this isn't from the book, but I wanted to bring this in to remember that they're used as storage devices. So excess fat is stored in these reserves, these fat reservoirs, and they're utilized until we need them. So they're more long-term storage. Carbohydrates in the form of glycogen is the more shorter-term storage of energy, and those get chopped up really quickly. Triacylglycerides, though, are a little bit tougher to use, and they're harder to burn off. So there are fat reserves, and they're also used as insulation under our skin. So thermal insulators and fat reserves, and they're stored in these adipose tissues under our skin. So that's where we find these triglycerides. So what do we mean by fats then? Well, if we go back to this picture, butter is a fat that comes from dairy products, milk. You can also get a Crisco or, well, actually that's vegetables, but lard, for example, that's fat that comes from pigs. And you'll notice at room temperature, they look like this. They're solid. Oils, these come from animal sources. They are also triacylglycerols, though. They're both mixtures of different types of triacylglycerides. So, but you notice they have very different properties at room temperature. And specifically olive oil, for example, olive oil comes from, olives, and there are a lot of triacylglycerides that are mostly unsaturated. So there's not that many saturated fats inside these oils, and we notice that because it's room temperature liquid. And there are not, if for a high quality oil, you do not want free fatty acids themselves. That would lend to an acidic quality, and you don't want that in your oils. You don't want free fatty acids flowing around. You want mostly intact triacylglycerides. So to do that, you need to be gentle with your oil and produce it in such a way that you're not forcing this over to break it apart. So you want to be gentle. You want to do a good job of producing the oils in a gentle way so that you can get mostly still intact triacylglycerides and not the free fatty acids. This is just another way this is just zooming in on here. And I wanted to note that the book, I believe, calls this the line angle formula or structure. And honestly, that's true. I'm really not used to hearing it called that. I always call this a skeletal structure or a skeletal formula, but they're both valid ways to depict this fatty acid. Remember, each point is a carbon, and the rest are hydrogens. So this one has 2 bonds to 2 carbons, so it needs 2 hydrogens coming off of this. That's why this is a CH3 right here, and this is a CH2 right here, and so on. And this COOH group is how we show that this is a carboxylic acid at the end here. So again, fats versus oils. The left-hand side, we've got a fat. The right-hand side, we have an oil. What's the difference? They're both mixtures of different triacylglycerides, but the issue, or not the issue, the interesting thing is that these have more saturated carbon chains. And just from a simplified perspective, you can think of these as stacking up next to each other. The van der Waals interactions between these and dispersion forces are much higher than these over here. Because of these cis double bonds, they form these kind of kinks, and these kinks go this direction. See how these are launching this angle here? So because of those double bonds, these don't stack as well intermolecularly as well as these. What that means is at a specific room temperature, it's going to take more energy to break these intermolecular interactions down. So this happens to be a solid at room temperature. It's not hard to cut through, but it is a solid, and this is a liquid. So that's really the only difference between these types of oils. Obviously, their flavor and their color and their consistency is going to be different, and it depends on with butter. There's salt that's been added, and there's other things in there. Oils are going to be more neutral. There's not a lot of flavors added unless you're buying like a flavored oil, for example. But those are the main differences between just those type of cooking oils, the things that we use. It's really that those cis bonds break this down into a liquid versus a solid at the same temperature. This is a good way to depict these again. These are kind of bunched up. I got this photo from the internet. This is from the book. So here we see these just single bonds everywhere, completely saturated. Versus, and you notice these cis bonds, they look kind of weird. They draw them kind of flat like this because if you didn't, these bonds would go way over here and these would go way over here, and it's hard to get on one page. But notice these still are cis. That means there's a hydrogen coming off here, hydrogen coming off here. That means the big R group, which is this entire thing, is going that direction, and this big R group is going the other direction. So that's a cis bond. So unsaturated fatty acids. And this really, the location of these double bonds and how many of them are in the structure really depends on where you got those oils from. So you'll see that there's mono unsaturated oils versus polyunsaturated oils. Depends on the source of the oil, what type of plant you got it from, what source. Yes, this is the better. I grabbed this photo from the internet too to really show you that this is how you would really start drawing that chain, to really show that it is going in this other direction. This just, even though this can spin around and get flatter, this just really shows you the directionality of that cis bond versus a trans bond would look like this. Trans fatty acids and trans triacylglycerides with trans bonds are very uncommon. There are a tiny bit because this bond can shift to trans given a certain amount of energy. It can happen, but very low percentage of this. Our bodies are, and the natural sources that we find have the cis bonds. This idea of taking saturated fats, unsaturated fats like oils, and turning them into like a spreadable butter, something that's more solid. Well, they took that idea and did something called partial hydrogenation. And we don't do this as much anymore, but this idea is we're taking some of the double bonds and producing a certain amount of single bonds. And I'll show that to you here. So think of a liquid oil. So let's say you're trying to make a solid spreadable butter that's not actually butter, because butter comes from dairy. So a non-dairy butter, essentially. If you take something like olive oil or canola oil, which has these double bonds in them, and you do a little bit of hydrogenation, not full. So maybe we do a limiting reactant here where we just have a little bit of hydrogen. This says nickel or palladium or some metal. This just represents there's got to be a metal here as a catalyst. What can happen is we can partially hydrogenate, as in we're going to reduce some of these bonds from double bonds to single bonds. So this is now a partially hydrogenated oil, essentially. Notice we got rid of, in this depiction, these two at the top, one in the middle, and left this one here. This is just kind of random. So it turns these into, instead of linoleic acid, now this is a steric group. And this was linoleic, and now it's oleic. So we've got two oleic. These come from these names are not systematic names. So this would be a solid at room temperature. So we essentially kind of made an artificial butter by taking liquid room temperature olive oil, and anytime we get these more saturated groups, this now it takes more energy to melt this. So this becomes a solid at room temperature. So I tried to look this up and find ones that have partially hydrogenated oils, but honestly, it's really hard to find that anymore. So I looked up Crisco, for example. Crisco, here's the ingredients from their website. It's solid at room temperature. It says 50% less saturated fat than butter. So what they're doing is choosing amount of oils, in this case soybean oil. So they took soybean oil and also fully hydrogenated palm oil. So they took palm oil, which has a bunch of double bonds, completely hydrogenated it, and then they also took normal palm oil. And then they also just took some different diglycerides and then used to give it some texture, I'm assuming. And these are antioxidants to keep it from going rancid over the long term. But what happens if you do partially hydrogenate? This is not a great thing because, this idea of partially hydrogenating was to, improve the shelf life of vegetable oils and basically make new cooking products. So when you take something like this, unsaturated, and you hydrogenate it to a saturated compound, sure, but what can happen is this can interconvert between cis and trans in the process. So this is where we get all of a sudden, during our partial hydrogenation process over here, this is ideal. We keep all of our cis bonds, but some of them could be transferred to trans bonds, and those are not natural fats. Our body does not really know what to do with the trans bond. We don't process it in the same way. So there's a lot of research out there showing that it's not healthy to consume trans fats. So that's why you see this on these labels now. Zero trans fat. It's a huge deal to put that on a label. The problem is, though, with these products, zero trans fat means if there is less than 0.5 grams per serving, they can get away with calling it trans fat. That number can vary wildly between products. Some products maybe have 0.1 grams per serving. Some products might have 0.47 grams of trans fat per serving, and that's a lot. So kind of got to be careful with what you're eating and depending on what the source of their hydrogenation process is. But I really couldn't find any labels that said partially hydrogenated oils anymore. Like, if you find one, let me know, because I'd be very curious. But I did a lot of searching on different types of butters or different types of spreadable butters like Land O'Lakes and Country Crock, and I Can't Believe It's Not Butter, and all these different brands of spreadable quote-unquote butters that are dairy-free. But it seems like the industry is really pushing away from partial hydrogenation and instead using different emulsifiers and stuff to make these oils into more of a solid form at room temperature. So that's a little jaunt through the world of the problem with trans fats. Now, just to give you an idea of different melting points and freezing points of different types of butters and oils. So let's take a look at just your normal butter and the percentage of unsaturated. fairly low percent. Still 33% of the triacylglycerides in butter are unsaturated, but that means that 67% are saturated. That lends to a higher melting or freezing point. So as in, it takes 35 degrees Celsius to melt this stuff, or 95 degrees Fahrenheit. Clearly much high above room temperature, but not that hard. You put this in a pan, a warm pan, butter starts to melt very easily. Coconut oil, on the other hand, only 9% of it are unsaturated. So you would think that this would even be, even more solid at room temperature. Actually, this is a little bit easier to melt than butter. Again, there's a lot more that goes into the melting point of butter than just the percent unsaturated fatty acids. But clearly, both of these have a very high amount of saturated fats. So again, coconut oil, you'd have to get up to 77 degrees Fahrenheit to start melting that. Now check out these oils down here. Canola oil, soybean oil, and olive oil. They are clearly, the vast majority are unsaturated, and very little saturated fats that come from plant sources. So to basically, I put the freezing point to give you an idea too, and it's the same number, but I turn this into Fahrenheit. To freeze canola oil or soybean oil, you'd have to get it down to -10, -16 degrees Celsius, or 14 degrees Fahrenheit. And to give you an idea, the temperature in your fridge is about 35 to 38 Fahrenheit. So you could put, these oils in your fridge, and then they're still going to sit there. They're not going to solidify. One way to really actually investigate that is go find a bottle of oil-based salad dressing in your fridge and take a look at it and look at the ingredients, see what type of oils are in there. Probably you're going to be seeing a lot of these type of oils, canola, soybean, olive, etc. And they're not going to be frozen in your fridge. They're nice. They're still liquid. Put them in your freezer, though. Freezer's probably close to -18 Celsius. You'd probably be able to start freezing your oils if you put them in the freezer. So you could try that as a little experiment, be like a little spoonful of olive oil in your freezer, see what would happen. But this percentage of fatty acids really helps determine, you can help predict the melting/freezing point of some of these oils. Again, these sources, butter and other fats, think of bacon grease, for example. When you're rendering down a piece of bacon, you get all that oil in the pan, and then when you let it cool to room temperature, and you get this solid mass. That's because in bacon fat, like from other sources from animals, there's a lot more saturated fat that comes from animals. So bacon fat, pork fat, beef fat, you put a nice, delicious soup in the fridge that you made with beef, and you get this layer of fat on top. That's because you're solidifying those saturated fats that are coming out of the solution. Here's another way to depict this. I pulled this graphic as well. Olive oil, again, like 86% is going to be unsaturated. That's what these green ones are. C16 to C18 long, and there's also some C4 to C14, some shorter ones. Just a few of those in olive oil. Butter, though, you got this really kind of interesting mixture. A lot of saturated, but still quite a bit of unsaturated as well, but big chunk. This is beef fat, so this is like a hard solid versus butter's fairly soft at room temperature. Yeah, beef fat is going to be almost half of it is saturated, so quite a bit different than just butter. And this I pulled up lard from pigs. This is a great cooking source. People are kind of afraid to use lard. I think it gets a bad rap, but it's a natural cooking source. And back in the day, we used to use this a lot more. And it's just fat rendered from pigs. And it's a great cooking source. And it's solid at room temperature, but it's got very good cooking properties, and it gives that kind of nice porky flavor to your stuff for frying, things like that. So that's what all lard is. It's just a different type of fat. You can go through these questions on your own. It's using percentages of unsaturated to saturated fats to kind of predict properties of things. So example 23.6, go through that one in your book. And yeah, try to visualize from what we learned about those double bonds and things like that. Okay, so moving on to the next classification of lipids. I told you it's quite broad, but you'll notice some similarities between these compounds. Phospholipids are ones that instead of just having a non-polar nature to them, they really have this polar group. So instead of just glycerol, notice, if you look in the middle here at the structural kind of skeletal formula, you'll notice we have this glycerol backbone again, right? And we have two fatty acids, maybe one of them saturated, maybe one of them is has a double bond on one of them, but the other side has been replaced by this choline group and this phosphate group. So this would be phosphatidylcholine, I believe. So they all have their different names, but we have a phosphate and choline. And notice the charges here. These are very polar compounds here. So this is a very polar head. This is a very non-polar tail. So these act as like surfactants, or almost like soap molecules, essentially. So these are found in cell membranes. These are structural types of lipids. They're not really used for energy storage. They're used for structural components. And if we look at what one of those phospholipid bilayers looks like, this blue is water out here. So naturally, these are going to form nonpolar regions in the middle. The nonpolar tails are not going to favorably energetically interact with the water, but the polar head groups will. So we form these bilayers, and this is the most basic form of what a phospholipid bilayer of a cell membrane would be. These are going to protect the cell. They're going to allow transfer of things inside and out of the cell. Within these, there's going to be lots of different transport proteins and other signaling molecules. There'll be cholesterol groups in here. There'll be a lot of different types of things in here, but this is the basic structure of what phospholipids do to form those bilayers. And finally, the last classification of lipids, again, this might not look like a lipid, but I'll show you why it is, are steroids. Or not the last, but one of the last ones. Steroids share this ring structure, 5, 5, 5, or sorry, 6, 6, 6, 5. If you see this, what we call the nucleus of the steroid structure, or if you see this 5, 5, or 6, 6, 6, 5, you should know that that's a steroid type molecule. Steroids, as classically known as people getting jacked in the gym by using steroids. Yeah, they're taking steroids. They're very, very powerful compounds. You only need a little of them. They're molecules that tell other parts of the body what to do. So they're signaling molecules. That they also are, another type of steroid, cholesterol, is a really important cell membrane as well. So they share different types of properties as phospholipids as well. And cholesterol is really important to the transport of lipoproteins to the body. So cholesterol specifically, notice it is a steroid. This is not, though, like that hormonal type signaling molecule really. But notice that it does kind of share the structure of a lipid, or those other lipids, in terms of you have this polar head group here. It's not very large, just an OH group, but it is polar. And then notice you've got this really non-polar region here. So it does also become a structural component of cell membranes and things like that. So what about other hormones? So steroids, and again, you've heard of steroids, I'm sure. But yes, lipids can be hormones as well. So steroid hormones, we might see reproduction hormones, a growth, regulation of growth in your body, like muscle growth, immune system as well. So very, very important to all those systems. Yeah, they help communicate. They go out into the blood and help communicate between cells. Prostaglandins are another type of hormone, and they have a different type of core to them. We'll look at that in just a second. They are important for another variety of factors. Blood pressure, one of them, that's really important. Also, inflammatory response. They are responsible for eliciting that response when you get injured, things like that. So thinking of prostaglandins as inflammatory increasers, if you see the word NSAID, NSAID, or non-steroidal anti-inflammatory drug, you can use steroids to help with inflammation. But if you don't want to go to a doctor, rather, these are less powerful, but they're still very effective. Ibuprofen, naproxen, aspirin, would be something like Advil or Aleve. These are all compounds that help block the formation of prostaglandins, the ones that are involved in inflammation. So if you can ingest a drug that helps block the formation of these hormones, we actually help keep the inflammation down when sometimes it gets too high. Our body can go a little bit overboard sometimes with inflammation. So we use these as common drugs to do that. And these are the structures I wanted to show you. Here are some examples of the steroid hormones that do other things in our body. So again, anti-inflammatory, but they're non-steroidal. These are steroidal molecules that could go into our body. And you can get prescriptions for these. These are naturally occurring, but you can get prescriptions for these if you're really in bad shape, especially for something like arthritis, where you have really intense inflammation in your joints. you might be getting a shot of cortisol or taking prednisone. On the other hand, aldosterone, this one that can help sodium and potassium levels in your body. So that's another powerful hormone. So sometimes we actually ingest extra amounts of these, but you need to be very careful because these are very powerful. And you just need to be very careful and make sure you're talking to your doctor about whether or not these are needed or not. Here's some examples of the prostaglandins. So they share this type of structure. So if you see this 6665, think, okay, these are steroids. Prostaglandins don't have this interesting side here. It's this 6,5, and you'll see some OH groups, maybe a carbonyl, and then these other side chains. These are very indicative of what prostaglandins do. And again, I don't exactly know what these do, but they have a very broad classification of stuff that they do in our bodies. And here are the summary of these lipid types. So again, triglycerides, think energy storage and insulation. Remember, I'm not fat, I just have a lot of insulation. Yes, but it's true. Yeah, we need insulation and we need these fats in our body. They're healthy to have. So this is glycerol, 3 fatty acids. They can be saturated or unsaturated. Phospholipids are membrane components, and they've got the glycerol backbone, 2 fatty acids, and then just they have this other polar charged group on there. Steroids have that characteristic 4-ring structure right here. And they can help with all types of hormonal things in our body, inflammation, growth, and also cholesterol is a specific one that helps also with the cell structure and also transport of fatty acids. So cholesterol is really important. And then prostaglandins is another category, more hormonal type things in our body. So very important to understand these as a chemist in general. I love talking about this stuff. I love looking at structures. I love looking at functions of molecules, and we just scratch the surface into the world of hormones and lipids and fatty acids and things. So if you ever get to take biochemistry, you're going to dig into this stuff a lot more. And with that, here's a little bit of practice for you guys, using this to identify what is what by what you learned. Go ahead and go through that and go through the examples in your book. And we are out of here for section 23.3. So if you enjoyed learning about the wide variety class of lipids, the next time I see you guys, we will be reminding myself amino acids, peptides, and proteins. And that should be our final section. We will not get to 23.5. So first 4 for our next exam. And I'll see you guys then.